And our first speaker is Brianna Wren from University of Maryland. She's going to tell you what she's talking about, but I'll tell you some fun facts. One is her favorite part of working on this paper was Jeff never got mad at her. The second is that she's trying to graduate next year, in which case she'll be looking for a job. So if you have a job, you should talk to her. I mean, like a job for her. So now, yeah, take it away.
Okay. My name is about just-in-time static type checking for dynamic languages. This is Jeff Foster. To motivate our work, let me show you a simple example. Here we have Rails, which is a web programming framework for Ruby. We have a class called Talk, where each Talk instance database. Inside Talk, we have defined a method that takes one argument user and checks if user is the Talk's owner. Now we want to be able to type check. Problem is, if you look through the rest of the code, which find an explicit. Now let's look at the belongs to is there to specify owner as Talk, and that owner should have. Belongs to takes two arguments, owner, which is symbol or an integer string, and the second argument is a hash that maps class name to user. The belong dynamically generates the owner method. This is an example of metaprogramming, where methods generate other methods on the fly. Metaprogramming is used all over the place in Ruby on Rails. Programming can occur at arbitrary points during execution. Now, in a purely not even type check the simple owner question mark method unless we understand what this metaprogramming code does. To solve the metaprogramming problem, we propose just-in-time type checking. We have type annotations that execute at runtime, and calling type stores the type information in a global table. We also extend metaprogramming to also generate types as methods are created. As you will see later, this is actually easy to do in practice. In addition, we statically type check the method body when it's called at runtime, using the current global table, and we use caching for better performance. Implemented just-in-time type checking in a system for Ruby called Hummingbird. To evaluate our idea, we applied Hummingbird to 6 applications, including 3 Rails applications, 2 other metaprogramming applications, and 1 plain application that does not use any metaprogramming. We found the performance overhead is reasonable. We have a between 5.7 times performance overhead, and all type checks successfully using Hummingbird. In addition, we found that our performance. We also applied Hummingbird to our application, and we were able to catch a couple of type bugs. At the end, we applied Hummingbird to 1 Rails application as it was updated in development mode to test cache invalidation. Tell us about those experiments. Now let's get back to the owner example. We have the belongs to call at the 2 arguments, a symbol and a hash. Now earlier, we developed a system called RDL, which is a Ruby contract system that allows us to add pre and post conditions at runtime. The pre method is what allows us to add, and pre takes a code block as its argument. It's simply an anonymous function delimited by do and. On top, we wrote a pre-contract for belongs to and options, and those arguments are the actual arguments. Now let's look at the code block body of. First, we convert the first argument from a symbol to a string. Next 2 lines compute the type of the foreign key. And the type is going to be the value of the class name if we pass 1 in, or it's going to be the first argument singularized and then camel cased. The last 2 lines add types dynamically. We will add the type for the foreign key getter and 1 for the setter. In our case, a type for owner and a type for owner equals. Now let me show you. Here we call this constructor of struct and names as symbols, and we store the result in a class called transaction. The dynamically create a getter and a setter for each. We want to be able to add types for those attributes. We could have called type 6 times to individually add the types, but a better way. Since Hummingbird allows the programmers to write arbitrary code to generate types, we wrote the add types method below. Add types takes the list of attributes arguments, and inside add types, we pair this annotated type, and then we add a type for the setter. After we call add types on the transaction, the type check code that uses one of the getters or setters. Now that you have, let me show you the core calculus to capture just-in-time type checking. Then I'll tell you more about the implementation. It's Hummingbird in a core Ruby-like language, and our language is mostly standard. That can be nils or objects, and then we have expressions that can be values, variables, sequencing, new objects, conditionals, or function assignment applications. But our system also has two novel expressions, and we have highlighted those two expressions. The first novel expression is our method definition. Now, if you look at it closely, you can see that we allow a method to be defined inside another method definition. And can occur at arbitrary points during execution. Our second novel expression, which can also execute at runtime. So when we have a function application, we statically type check the body of the method, and we cache the resulting type check proof for future reuse. Here's the judgment form for our static type checking system. On the left, we have TT, which is a type table mapping methods to their types. And this table is updated at runtime. We have an initial experiment gamma, the expression E that we want to type check. And then we get a new gamma prime, which is and T, which is the type of the expression. Here is what allows our system to be flow sensitive, which is important for Ruby. Our static type checking rules are standard, so we won't show them here. Now let's look at part of the configuration semantics. First, we have X, which is a cache mapping the method names to their type checking. TT, which is the type table, and the DT, which is a method definition table mapping methods to their definitions. And then we have expression E, the expression we want to evaluate. Most of our dynamic semantic rules are also standard, so I'll just show you a few cases. Let's first look at how a type annotation would work in our system. On the left, we have X, the cache, TT, the type table, and then we have the type annotation. On the right, we have the same cache, but we got a new type table that has the type annotation added. Annotation evaluates to nil. Method definition works in our system. On the left, T, which is the definition table, and then we have the method definition. On the right, we get a new cache that's the same as the original cache, but it has the existing type checking proofs for the method removed, along with its dependencies. Now, if method A calls B, then B is a dependency. And also on the left side, we have type table. That's the same as the new DT, which has the new type definition stored. The method definition evaluates to nil. Now let's look at how a function application would work in our system. In the configuration and the function application, the method name is a.m, and the actual argument value is called B. Before we are able to type check this function application, we assume that we have already stored the type of the method in TT, which is the type table. So first, we check if the runtime value of the argument is a subtype of its annotated type. So we won't type check the rest of the code. Otherwise, we'll look in the cache and see if we are with that method stored. If yes, then we'll directly the current environment. Otherwise, we will type check the method body using the standard type checking rule. And if it doesn't type check, we'll get an exception. Checking proof to TT, to X, which is the cache function application. We also that says well-defined methods do not go wrong at runtime. They don't call methods with bad argument names. Some errors to happen at runtime, including invoking a method whose body does not type check at runtime and calling a method but is itself undefined. The formalism, let me give you an overview of our implementation. Hummingbird relies on two existing systems. RDL, which is the Ruby contract system. That is the system that I introduced earlier that allows us to add pre and also relies on RIL, the Ruby intermediate language, or real. Here we have a method definition for foo. We first use the real parser control flow graph of that method body in a JSON file. And then we use RDL to modify the original method to have type checking. So in the modified foo, we'll first type check the actual runtime value of the argument, and then we'll statically type check the body of the method. And finally, we will run the original method. And during the static type checking, pre-stored control flow graph. We have also implemented cache invalidation in Rails development mode. In this mode, Rails automatically reloads modules server restarting. Our current implementation, but for Rails development mode, of cache on reload, we record method has been changed or deleted, then we remove that method along with its dependencies from our cache. Also supports typecasts, and here is an example. We annotate partial.load to have, and then we annotate the class variable cache to have type partial.load, and we store its result in the class. We will actually have a type error here. We have type object, which is not a subtype of the left-hand. To solve this problem, we use RDL cast. Cast the right-hand side to have type checking. Hummingbird will assume the right-hand side. But at runtime, Hummingbird will check if the right-hand side value is actually. We open a couple of applications and we run our experiments on unit tests to invoke the actual method call. Came with the applications, or we wrote them with the goal of covering all. And again, we run Hummingbird on 6 applications, 2 other metaprogramming applications don't use any metaprogramming. We use many type annotations. There were that we did not type check, including common Ruby methods, types generated by common Ruby contracts like the one for belongs to, and also we did not type check application-specific Rails helper methods. We did type check the application methods that we. And this is a table showing our type checking results. First, we counted the lines of code in every application, and those range from 84 to over 1,000. And then we measured the static. First, we measured the number of methods that we actually static call. Those range from 14 to 127. And then we measured the number of checked plus types with trusted annotations. And finally, we measured the checked methods plus the Ruby core and standard library types. Numbers, we measured the numbers of dynamically generated types and dynamically generated types that were actually used. Owner example, we had this belongs to contract that generates one for owner and the other for owner equals, but only the owner type was used. Okay, if you look at the last application, it doesn't have any, just because that last application doesn't have any metaprogramming. And we measured the number of casts used in each application. Number of casts, and those were used for adding parameters to raw generic types. And here's a table showing the performance of Hummingbird. The original running times of the applications. We measured the running times with Hummingbird, but we measured the running time with Hummingbird and using caching. And the last column shows between the original and Hummingbird columns. As you can see here, in your system, if you look at the pubs data, the data for pubs, you'll see 20 times slowdown when we didn't use caching. And also, if you can see that the last two applications, because they spend much time with intercepting. On the other hand, if you look at the first three applications, those are Rails applications that spend the framework, Rails framework code that's not intercepted. We also performed another experiment where we applied Hummingbird to earlier version of one Rails application. A co-author actually wrote this application called Talks. He introduced some bugs, and I was able to use Hummingbird to catch several bugs. All the bugs I caught. The first one is a place where we have a name that was not spelled correctly, and the second bug here is a bug. This is and this is probably the most interesting. It actually silently ignores extra blocks at random. So using pure static analysis, pure dynamic analysis, we would not have been able to catch the second bug. And the third bug is to a method that was expecting a symbol as its argument. And the last method on an object that does not have that method defined. So at the end, we performed this Rails live where we launched one version of Talks and updated it to 6 consecutive versions to test. And we also performed this last experiment to show that we can type check versions of a program as it's being updated. Is especially useful here since usually only a small number by each update. So the second column in the table here lists the number of modified methods. And as you can see here, for half of the versions, only one by each update. And then we measured the number of methods, and we only have small numbers here. Numbers of dependent methods. There wasn't any dependent methods. This column shows the number of methods that we had. Included the methods that were modified and For the initial version, we show 70 that were checked. And for the subsequent versions, we show 2 numbers. We had this limitation in our implementation so that some module helper methods were always rechecked. And so the show the number of methods that were rechecked because we on the right shows the number of methods that were would have been rechecked if we didn't have this. So in conclusion, we Hummingbird, which is a just-in-time static type check. Type information is tracked dynamically, method time when they're called, and we found that it uses metaprogramming generated methods and eliminate redundant method checks. That's it. Thanks for coming.
Thank you, Brianna. Are there questions? If you have questions, please come up to the... So I have a first question. What are the parts of Ruby that are slower to check if they want the type checking to be fast?
Probably, I mean, a lot of things are going to be typecasts, then the runtime type check at runtime, so that might slow things down.
Here again.